Good morning, calculus.
Hey, good morning.
Good morning.
Welcome to the calculus of parametric equations. We got to launch a little further. You may have noticed that your online homework assignment kind of had two sections, in the sense that the first part was sort of more just, do you understand how to convert back and forth from polar to from parametric to rectangular coordinates. And the second part, which we need to talk about today, was a little more towards the calculus itself. So let's launch in. We got some cool stuff to talk about. And let's start with, I don't know. Let's start with this guy. So take a look at this graph. So here's a, I don't know if I want to say typical, but a nice, typical in the sense that you will recognize it. What is this graph? So the x coordinate, x equals, is 2 sine of t, and the y coordinate we'll just say is the cosine of t. What graph does that produce? We'll save time and let technology take care of it for us. So notice again, the default in Desmos is to let the time go from, I like to think of it as seconds, 0 to 1 seconds. So that thing is kind of flying. And as I showed you yesterday, it's kind of fun just to throw in a constant for C. That way you can actually watch it move. And so interestingly, this thing actually, it starts at 0, 1. And of course, if you think about that, that makes sense. So at time 0, sine of 0 is 0, cosine of 0 is 1. So yeah, that would be at the point 0, 1, wouldn't it? And so it actually starts there. And then its directionality is actually, I guess that would be clockwise. So it's cruising around in a circle and it gets back to the start. Notice it seems to get back to the start at 6.3. Does that look familiar to you? Shouldn't be surprising what it takes to make that make a full lap. And so that's actually taken a full lap, 2 pi, in order to make it all the way around. So notice that actually makes an ellipse. That's kind of fun. So this is what an ellipse looks like in this form. You may remember what an ellipse looks like in rectangular form. But apparently it takes 2 pi to make it around. Now, my question to you is, what's happening when I get past 2 pi? Notice my constant is out to 7 and I don't really see the graph changing. Is the graph changing?
It is. It's still going clockwise.
Yeah, it's on top of itself. It's just cruising around in circles. Now, this is what's really important in a practical sense about parametric equations, because we are flying around the sun in the shape of an ellipse, and we'd like to go more than 1 lap. And so it's relapping it. So it doesn't make any more of a graph. So in rectangular, you'd say, you're done. There's your purple ellipse. Good for you. You're done. But in parametric, it's actually continuing to follow the same thing. And that actually makes a difference. And so it's like, how many laps has it taken? And so, you know, you might be concerned with, as we're going to talk about today, like the arc length. And so you could say this went from 0 to 4 pi, which would be 2 complete laps, and that ask for the arc length. And that would be how far it had traveled in, you know, think of it as the solar system, like 2 years. And so it would have made 2 laps, and that makes a difference. So you don't just stop at 1 lap and say, what's the perimeter of this shape? And so sometimes graphs will land back on themselves, and then sometimes they won't. So that's kind of fun to think about. Let's take a look at this thing for a little bit and just answer a couple of questions about it. So let's see, is that good enough? Yeah, we'll say that's good enough. Let's bring it over. So could you, from yesterday, quickly find the horizontal and vertical slopes? Where is that slope horizontal and vertical? Notice it's really easy to see based on the graph. You could just cheat to answer this, but let's just make sure we can do it without cheating. I'm going to give you a head start while I make the graph look a little better, fit a little better. So 12.1. Focus a little more today on the calculus of parametric equations. So we technically would say, or it might be written as x equals 2 sine of t and y equals cosine of t. And of course, this would be a location where you have a vertical slope. And this location down here would be a horizontal slope. So can you do that from yesterday? Well, we said we know how to find slope. If I take dy dt and I divide by dx dt, the dt's will cancel out and I'll get dy dx, the change of y over the change of x, which is slope. And so in my case, if I do that, dy dt, the derivative of cosine is negative sine. The derivative of sine is cosine. So there would be my slope formula. I have a formula now to find the slope any place I want. And so as an example, the type of questions I could ask, we'll get back to vertical in just a second, but I could just say, you know, what's the slope? The easiest questions, like what's the slope at 1 second? So now that I have a formula for that, awesome. I just say negative sine. I want to be in radian mode, since that's what everything will be in. So I say negative sine of 1, boom, divided by 2 cosine of 1. And I'll just get, because 1 is not a nice angle, 1's kind of in a weird location, I get negative 0.78. I get approximately negative 0.78 for my slope. So it'd be kind of fun to know, you know, where am I at t equals 1? And notice based on that slope, I kind of know where I am. I must be over here somewhere, since I got a negative slope. And I could even probably do a reasonable job of guessing where that was, because this graph is still square. And so, you know, what's the slope of negative 3/4 look like? I could probably figure out pretty close to actually where I am. But of course, it'd be kind of fun to go over here. Oops, not over there. Be kind of fun to go over here. How can I locate that point? Well, yesterday I just kind of stopped the graph at 1, which is a good way to do it, and say, oh, I'm right there. There's where I am at time 1. That's where I am. Okay, the slope there, that does look a little steeper than -1. And so, okay, I can believe that. But you could also just graph the point. In other words, couldn't I just type 2 sine of 1, comma, cosine of 1, and actually graph that point, list the coordinates for it? And so even if I went past this to 2 pi, so that I had the entire graph, I could say I want the point 2 sine of 1, comma, cosine of 1. And I could say label that thing, and then I'd know where I am there as well. And of course, I can make that point slidable. I could slide that around too by putting C in there for 1. I don't know about you, but that slope looks like 45 degrees or somewhere in there. Notice a slope of -1 would have been 45 degrees. And so that's not quite as steep as 1. So it's a little flatter than 1, a little less than 45 degrees. So that all kind of looks right, I think. So foolish not to kind of check your work and play around and make sure you know what you're talking about. But of course, the other questions that are, you know, perhaps more interesting than just some random time and saying, what's my slope at that random time, would be to say, where is it vertical? Well, as we noted yesterday, and I will re-add to this note, when the numerator is equal to 0, that would be a horizontal slope, because the slope would be 0. No matter what's on the bottom, if you have 0/8, that's 0, then the slope would be 0. That makes sense. That'd be a horizontal slope. So let's go find that. So when is the sine? When is negative sine? This is the more interesting case where I don't say I know what time it is. I want to say what time is it when that is equal to 0. And you know when the sine is equal to 0, sine's a y coordinate, that would be at 0 and 2 pi, right, on the unit circle. I guess I won't belabor that point. So let's see, is that actually true? Is that working? Does that agree? Because isn't there 2 places on a graph that would have a horizontal slope? Up here as well. Yeah, at time 0, wasn't this right here at time 0? And we don't know necessarily about the second one, but it might make sense if you went all the way around the graph and got back to the start and it was 2 pi, that this would be time equals pi. And of course, I could quickly go back over here and say, slide this thing around, or just take it to pi directly. It's like, oh yeah, look, I am down there again. So those are the places where the slope of that graph would be 0. So that's kind of cool. And similarly, what if I wanted to know what is brand new for us, but a vertical slope? What about a vertical slope? So vertical slope is when the slope is equal to infinity, and the slope is equal to infinity when the denominator is equal to 0. So that gives you a vertical slope. Does that feel good to you? Or are you just writing that down? I mean, do you understand why dividing by 0 is actually infinity? I wanted to say this yesterday, but I'll say it really quick. If you had $12 and you had 3 friends, that's what division is, right? Like in a simple sense, you'd say, hey, I got $12, I got 3 friends, so I'll divide 12 by 3. And that means each friend gets $4, right? So that's really cool. Or you could say, I have $12. I think I'll divvy it out in $3 increments. I wonder how many friends I could give money to. So then you say, oh, that'd be 4 friends. Well, what if you had $12, but you divided it in $2 increments? Does it make sense? Now you can actually give it to 6 friends. What if you had $12 and you divided it into $1 increments? Well, then couldn't you serve 12 friends? What if you had $12 and divide it by 50-cent increments? Then couldn't you do 24 friends? Division is repeated subtraction. It's like, how many times can I subtract 50 cents from my $12 before I run out of money? And the answer is I can subtract 24 50 cents. Well, if you just kept going with that, what's 12 divided by 0? If you gave $0 to each friend, how many people could you give money to? It's like 0 for you, 0 for you. Hey, I still have $12. I'm not running out of money. Wow, at this rate, I could serve infinitely many people. I mean, do you see the logic in that? Dividing by 0 is infinity. It's not undefined. That's something that bugs me. I guess it's because I know calculus, but I understand why they say it's undefined, because infinity is not a number. We act like infinity is a number. But you have been studying infinity, and so you're a little more comfortable with this concept, and so it should make sense to you. You can always get these things to really understand. And so where's the vertical slope? Well, I just need to figure out when 2 times, since the denominator is 2 cosine, when is 2 cosine of t equal to 0? Well, when is cosine equal to 0? Cosine's equal to 0 at the top and the bottom of the unit circle. In other words, at pi over 2 and 3 pi over 2. That's where the cosine being the x coordinate, that's where that's the case. And so I won't go back to the graph, but at pi over 2, that's exactly where we were. We were on the right side of that ellipse at 3 o'clock, and 3 pi over 2, we're on the left side at 9 o'clock over there. And so that's kind of cool. We can find all those things. Let's do one more fun thing to this shape now that we didn't learn yesterday, and that is, what is the area? And I guess I will just say between 0 and 2 pi, since it took that much, and I guess I should say technically including those, since it took that much to just make the shape. And so I wanted to know what's the area inside that. And you may have in your travels learned the formula for an area of an ellipse. And I'll talk about that in a second, but let's just go get it. How do you find the area under a curve in parametric? Well, this is kind of fun. Let's build this for ourselves. You remember that to find the area under a curve, the principle behind it was this was a little bit of X and this was Y, right? And so we took those rectangles and we added them all together. So in rectangular, we said if we take Y and multiply it by a little bit of X, Y was the height of our rectangle, DX was the width of our rectangle, and then we just add a bunch of those together, then we'll have the area, right, between whatever points we want to know. And so how's that going to work in this world? Well, let's think about what we know here. So, what about parametric? How are we going to do this where there's t's? And so, well, I mean, isn't our y intact? In other words, isn't that our y right there? So can't I just use that? Like I'll replace y with cosine of t. But how am I gonna, so this will be, I guess you could say this will be our y as a function of t graph. I mean, it's still a y coordinate, right? But how are we going to get dx? Well, let's make a dx. So what about dx? What the heck is that? Well, we get dx by taking a derivative of something, right? It's got to have an x in it. And so don't we have the function, x equals some function of t? Again, in our case, that function of t is 2 sine of t. So it's some function of t. And then if I took the derivative of both sides, wouldn't that be dx equals f prime of t? Aha. Well, there's our dx then. If I take that dude and stick it in there, then there's my formula for how to do this in parametric. So area under the curve in parametric is actually this formula. It's kind of surprising. It's kind of neat. So I would say y, I mean, there's a number of ways I could write it. I'm just going to say the y coordinate is a function of t, and then times the x coordinate as a function of t, except for its derivative, and then it would be dt. Notice with respect to the chain rule, if you say, what's the derivative of f of t? It'd be f prime of t times the derivative of t. Isn't that what the chain rule says? Times the derivative of the junk inside. So there would technically be a dt there, and since I should have added that. So there's our formula. It's kind of interesting, isn't it? Like our little bit of x is actually a derivative. That's kind of cool. So this is an important formula for us to note. Okay, well, cool. Let's do this in our example then. So we say, okay, for us, for our apparently ellipse example, then I would say, okay, so the y coordinate gets left alone. We said the y coordinate was cosine of t. But we have to multiply that times the derivative of the x coordinate. The x coordinate was 2 sine of t. So the derivative of 2 sine of t is 2 cosine of t dt. There's our integral. If we can take that, and again, we decide where we want to go from. We could go from 0 to pi, or 0 to pi over 2, or pi over 2 to pi over 4, or anything we want to, but we're going from all the way from the start of the ellipse all the way to the end of the ellipse and just saying, I'd like to know the area. It's kind of like inside that curve, really, in this case, since it's closed. That's kind of fun that it's closed. And so, fine. I guess I could take the 2 outside, and then we are, if you will, disappointed to find a fairly, well, not simple integral to take. Now, the purpose of this class, in a sense, you might want to consider rebuilding this, but I'm good with you cheating as far as integral taking is concerned. Let me bring in some goodies here. So you may remember from previous terms, for instance, there's basic trig identities. I'll just quickly say this, but this trig identity right here that tells you how to switch out cosine squared. Here's a cosine squared, and if I switch it out for the cosine of 2x, that would mean cosine squared of x is equal to 1 plus cosine of 2x over x, I'm sorry, over 2. And so our problem is to find the integral of cosine squared, but the integral of this is much easier because it doesn't have a squared. And so that's the method by which you would solve this if you're in Math 252. And be good to bring that back. But the other thing we built for ourselves because of how much trouble taking integrals is, because you give somebody 6 months, they're going to kind of forget that that's a possibility, right? So people make tables of, like, you make it once 6 months ago, and then you use it later so that you don't have to rebuild it. You don't have to remake it every single time. So I'm in my integral table here, and I'll post this in both my open math and in, let's see, I guess that's probably just the easiest place to post it. I'll post it in my open math. So you can get to it. But aha, there's one good old number 64 on this particular integral table. It just tells me what the integral of cosine squared is, and I don't have to do it again. I already did that like 6 months ago, and so let's not do it again. Perhaps you can see what I just showed you a second ago. The integral of 1/2 is 1/2 x. The integral of cosine of 2x is sine of 2x, but then you have to divide by 2. So there's my integral. So I found that answer. And so if I evaluate that, then I'm good to go. So I'm going to snap a pic of that dude because my memory will not allow me to still remember it 10 seconds later when it goes into the notes, which is horrifying. Horrifying. You get up there. Cool. So I can say, awesome. I know it's time to switch colors. I know that the integral of this would be x over 2 or t over 2. For some reason, I want to write that as 1/2 t. And then plus 1/4 sine of 2t. And I'm going to evaluate that from 2 pi and to 0 and see what I get. And I am multiplying a 2 outside, and since it looks like it cleans things up a little bit, I found myself wanting to do that. At least, though, especially at this point in your study of calculus, speak this language correctly. If you have not taken the derivative, then fine. But once you've taken it, there should be no integral sign anymore. You have taken it, and the rule of thumb is to put brackets around it, or at least a line after it saying now it's time to evaluate. And that's just kind of code for stick 2 pi in, get an answer, stick 0 in, get an answer, subtract them. So remember, sine, you should be able to do this in your head, but sine is a y coordinate. Sine's a y coordinate. Y equals the sine of t. And so when I stick 2 pi in, of course, I'm going to get 2 pi when I stick it in for t, but then plus what? Well, the sine of 2 pi times 2 is the sine of 4 pi. So 4 pi is right there. Unfortunately, I'm after the y coordinate for that. So it's actually nothing. That's cool. And then I stick 0 in, and t is 0, 0. And then the sine of 0, I'm also here at 0, same exact spot. So I end up with nothing. And so I just get 2 pi. So that's kind of fun. So you mean the area inside that ellipse that we just made is 2 pi? Yeah, that's exactly what it is. Any of you Sharpies out there remember the algebra formula for the area of an ellipse? It's actually pi times the long radius, which is 2, times the short radius, which is 1. It's kind of like pi times radius squared, except for an ellipse has 2 different radiuses. So if it was a circle, it'd be radius times radius. Well, one way to think about this is, so the formula you would see online would be something like pi times AB, and the 2 would be the A and the 1 would be the B. And so there's the algebra formula for it. Hey, look at that, 2 pi, it's the same answer. So that's kind of cool. So we need to practice that a little bit because that was a fairly long process. Let's take a look at just one more thing that's kind of interesting about this, in light of the fact that, again, I like this because we're talking about movement now. Before, this graphs never moved. They just kind of were there. They were not there, and then boom, they're there. Whereas this graph grows as time moves along. And so, it's cool to think about. I just watched Interstellar the other day in 2000, I forgot, 16.
It's a great movie.
It was a great movie. I loved it. But a big part of that movie was like trying to fly to some other place, and you got to have a super good understanding of the fact that things are orbiting each other out there, because you can't fly to where it is, because by the time you get there, it's somewhere else. You got to fly to where it's going to be. And so the concept of everything in space orbiting around other things of larger size in an elliptical shape is really kind of key to this whole thing. And so, but one of the big parts of this is speed, right? And you're aware, right, that we're traveling around the sun at like 66,000 miles per hour. I would challenge you to go figure out the math. It's not that hard as to why that would have to be the case. Think about it, it's real simple. We're 93 million miles from the sun, and we travel at that radius, and it takes us 365 days to get there. So if you're going to travel a circumference of a circle in 365 days, and the radius of that circle is roughly 93 million miles. And I say circle because it is an ellipse, but it's roughly a circle. How fast do you have to fly around that circle in 365 days? Answer: 66,000 miles an hour. Wow. It's a little hard to accept, a little hard to believe. But we want to talk about speed. I mean, that's kind of the other thing that's fascinating about this is, of course, if this is modeling something, then, something that's flying around, I think speed is a fascinating question that we really don't want to ignore. That's kind of the whole purpose of suffering and rewriting things in parametric. So speed or velocity, and then physics people get freaked out about these being different, and they are. But speed or velocity. And so notice in our case, let's go to some other location like 2. Time is 2, and just kind of figure out what our speed is. Well, notice you have kind of dx dt. You have 2 different speeds. You have kind of your horizontal speed, which would be dx dt. We figured that out a while ago. Let's see, the original problem was 2 sine cosine. So dx dt was 2 cosine of t. And so we're not dividing these to get a slope. And that's the thing that's kind of important you understand here. Slope isn't actually that interesting in these problems. What slope am I at? If I'm flying around out in space in the shape of an ellipse, I don't think slope is an interesting question. It's a question we can answer, but speed is a more interesting one. Well, notice this is your x speed. So if I say at t equals 2 cosine of 2, that's pretty easy. I end up with negative 0.83. What does that mean? If x is a length in feet and t is a time in seconds, that'd be feet per second. But what does the negative refer to?
Direction that you're traveling.
Yeah, it's left. Basically means you're going left. We'll go look at that in a minute. So at 2 seconds, I must be, heading back the other direction. Because remember when we drew this thing, we were going right for a while, and then we were going left for a while, and then right for a while. So this is actually saying you're going left right now at a certain speed. So that's kind of cool. And then the vertical component of your speed, of course, would be the derivative of our y coordinate. Since our y coordinate was cosine, the derivative would be negative sine. And at t equals 2, negative sine of 2 comes out negative as well. What does that mean? That means you're going down directionally. So we're talking about the y direction. So we're actually traveling left and down.
That's the fourth coordinate, right?
I like how you're thinking. So where would I be? Where am I if I'm traveling left and down? Raymond says fourth quadrant. I think he's right, isn't he? Aren't we over there somewhere? We must be over there. If we're at 2 seconds, we must be over there somewhere, because that's the only place we're traveling left and down. And just because we can and should, if we go back here and throw 2 seconds in here, yeah, there we are. We just kind of turned the corner. So that's technically velocity has a direction, whereas speed does not have a direction. So the fact that there's negative signs in there, these are velocities. And so your book assignment will correctly say, what are the velocities? And therefore negatives matter. But for you physics people, what if somebody actually wanted to know? What if somebody wanted to know the speed? Because if you're in a car, you just kind of look at your speedometer and it's like, that's how fast I'm going. You don't think, well, I'm going this many miles an hour horizontally and this many vertically. You just put them together. Well, how are we going to put these together? Think about what this looks like. If in the X, we were going negative 0.83, and in the Y, have you studied vectors at all? We were going negative 0.91, then that right there would actually be your speed. It's kind of a hypotenuse in the right triangle, if you will. And so that tells me, oh, I just need to do Pythagorean theorem on these two things. And so then notice that Pythagorean theorem would cleanse those negative signs because we're going to square them. And so that's just saying this is how fast you're going without direction included. And so that's kind of interesting. I don't know if your book assignment asks you about speed and velocity, but it's kind of.
We did get a problem on the homework.
Asked both. Cool. Did
Yeah.
it use the word speed?
It did, and it used that equation right there.
Cool. So whatever, I guess I'll write feet per second on this just because it seems like speed should have a unit. So that's how fast you're actually going right there. And so it's kind of interesting to think about, how fast are you going? Are you familiar with that kind of concept? When you whip around the corner, you're actually going to speed up. I don't know if you've water skied or all kinds of things like that. But speed is directionless, and so I would actually expect your speed to be the fastest, kind of over at those places where it's real sharp, like on the left and the right side. But you're not going to be traveling the same speed the whole time. Well, maybe you are. I guess we don't know. I think you're not, but I have to think about that to double check it. So that's kind of cool. Should be able to calc that. So the interesting thing is you don't actually have access to directly to your speed. You actually can only get the y prime of t speed, which would be vertical speed, and x prime of t speed, and then if I Pythagorean theorem those two numbers, then I'd get my actual speed. So that's kind of cool. All right, we beat that illustration to death. No, we didn't. Let's do one more thing. What about 6, the distance you travel? I mean, I think that's an interesting question too. How fast am I going? But how far is it to fly around that? What's the perimeter? The perimeter is sort of the technical word. When it's a polygon, it has straight sides. But when there's curves, that term is usually changed into arc length. It's a curve. So, how long is it? And again, that's one of the things we can do in calculus. If you're just a geometry student, you can only find distances that are straight lines by measuring them and maybe by Pythagorean theorem. But we got a curve, very hard to find distance. Without calculus, you have to kind of stretch a string around something and then straighten it out and measure the string, which is wonderful. But how would that work? How would we get arc length? And we talked about this. We talked about a formula for arc length back in Calc 1, because that's an application for, no, it was Calc 2. That's an application for both derivatives and integrals. But let's figure the formula out ourselves. This isn't actually that hard. How are we going to find arc length? Well, if we have a particular place that we're cruising along, and so in a sense, that length right there is kind of a little hypotenuse. As long as we keep it really short, then that would be straight, right? If we keep it really short, if we put those 2 points really close together, that would be straight. But in order to get that length, I would have to kind of do a Pythagorean theorem on these two sides right here. But what would those be? Well, isn't this one just like last term? Isn't that a little bit of y? Remember, the d means a little bit. That's a little bit of y, or the change of y. And this is a little bit of x, or the change of x. Well, we can find those in our world. We can find them relative to time. And so there's no reason I couldn't just say this is dy dt. Since what happens as I travel in this direction is a little bit of time has changed, then I want to know, how has y changed with respect to time? If that's a tiny change in time that moved me from one point to the other, then that means those lengths would be dy dt and dx dt. So then Pythagorean theorem would say, if you take those values and square them and add them together, then you would have the hypotenuse. But remember, what you have there is, well, one hypotenuse. You have that one tiny hypotenuse right there. What do we need to do? We got to add them all together. We got to add a whole bunch of those hypotenuses together. That's all integration is, adding up lots of stuff. And then there'd be a dt out here. So that's our formula for arc length. And of course, I could, write this a little nicer by just calling that x prime of t or something. And I could call that y prime of t. Fine. Okay, so that's kind of fun. Let's see if we can find the arc length from t equals 1 to 3. Now let's go 1 to 4. I don't know why, but let's go 1 to 4.
Wouldn't you have a square root in your
Yeah, didn't I forget something? Pythagorean theorem says square them and add them together, but don't we also need a square root? Forgot the square root. Thanks for rescuing us, Ben. I hope more than just Ben was thinking about that, by the way. So that square root's really important. Okay. So let's see, I need to take the derivative. Uh-oh, this seems like it could be really ugly. We just did the derivatives, right, back here. So I'm just going to look up there. So I need to evaluate from 4 to 1 dx dt squared. Dx dt was 2 cosine of t squared, plus dy dt, which was negative sine of t. That also needs to be squared. And to highlight my previous oversight, don't forget the square root. Now, because you're taking derivatives and square rooting, a lot of times the integral that you just wrote right there, and you may vaguely remember this from 252, but this often the process of taking derivatives, squaring and square rooting and adding and so forth creates integrals that you can't take very easily. So if it's a canned book problem, they have to work pretty hard to come up with a parametric equation for which you can actually accomplish this. But again, I would say this is not emphasizing that. And in a sense, maybe we don't get lucky in this problem. If we squared both of these, we'd have 4 cosine squared plus sine squared. So that's almost sine squared plus cosine squared. If I could replace sine squared plus cosine squared with 1, perhaps you remember that identity, then maybe I could have pulled this off. But unfortunately, that's 4 cosine squared plus sine squared. And so I'd have to work a little harder. Does that make sense? And so at this point, it turns into a math 252 problem, which is either very difficult and yet doable, or perhaps very difficult and not doable. And so we could lose a half an hour now by just kind of trying to see, is there some way I could actually take this integral? Could I do that by hand? Is there some way to do it? Again, from algebra, you might think, oh, look, squareds and square roots, I'll just cancel them out. You can't do that. That's a screwing up the order of operations. I hope you know that. But remember, in the kind of real world, people aren't, if you're a true mathematician, you'll be bothered by, is there a way I can take this? And perhaps you would go into one of my favorite websites, CY Math. And I think I'm going to go try that really quick just because it might be fun. Cheat websites. Let's see if, so the two of them that I'm aware of are CY Math and Wolfram Alpha. Let's just go bust out the internet and see if we can get it to tell us an answer to this. But if, remember, worst case scenario, as long as an approximation is acceptable, we can just go to Desmos and ask it to do this for us, right? So let's see how hard this is in the interest of time. CY Math is a great place to cheat if you aren't good at something in math, because not only does it give you the answer, it also gives you the steps. Let's see.
Do not encourage cheating.
Well, I just want to let you know that I know this exists. But it's a problem mathematicians are wondering about. Let's see, I'm not exactly sure how to type this in. Square root SQ.
It's SQRT, and then you just do 2 parentheses and put what you want in the parentheses.
Yeah. I thought you just said not to cheat. You sound like you've been cheating.
It's Logitech. It's what I use to write my projects. It uses the same format.
Yeah.
There's the keyboard button right there. I think it might have a square root in it.
Yeah, but
Or maybe that.
yeah, I bet you're right. And notice negative sine of t squared is just sine of t squared. And I'm a little concerned about and one of the things I like about this is it shows you what you just typed to kind of make sure you didn't blow it. Let's see. So I did blow it because I squared the 4 since I knew it was squared, but then I put it in there being squared yet again. And so I shouldn't do that, I guess. So there we go. And so awesome. And how come it isn't doing it? Well, I think I just need to hit enter and see what it says. All right, love it. So it said, sorry, too hard, can't do it. That's kind of what my intuition was. I didn't think it was going to be able to do that. So that's kind of a hint that not good. And so, of course, the easy way to do this is just to go into Desmos and type it. If you type int for integral and you say, I'm going to do this baby from 1 to 4. And again, you type the usual SQRT, except it immediately shows up as a square root, which I think is an improvement over what CY Math said. And then I go say cosine, and notice it doesn't actually matter what I say here. I could say t or x or anything. And let's see, I need to close that parenthesis off and square that, get out of that and say plus sine of t squared. And you may remember that it doesn't seem to want to do it. It doesn't do it until you put dt in there. And so there's the perimeter, or the distance, the arc length from 1 to 4, 4.64. So of course I should add that to the notes, and then we'll go back there. All right, Desmos on that. But before I leave here, just because it might be interesting, I wonder, is there a formula for the arc length of an ellipse? I think the answer to that is yes. But I do not, off the top of my head, remember what the formula for that is. And remember, our ellipse had a kind of an x radius of 2 and a y radius of 1. And so there's a formula for what you do with the 2 and the 1, and it'll produce that distance, but I just forgot what it is. Kind of a cool algebra formula. But anyway, that would be the entire circumference. So, if I was flying around the sun, I might want to know, what's a complete lap? What's a complete lap around that? Well, it's about 9.7 feet or whatever that is. So that's kind of fun. Is your brain okay on all that?
Isn't there a way to do it on your calculator also and get a decimal like that?
Yep. Yeah. Under the calc button. So if you type the function in there, graph it, and then you say, let's see, which was it? Yeah, calc right above trace, second calc, then you can do the graphing calculator too. So as I said a lot to a number of you just joined me in our little run through calculus, but I'm not a true mathematician. I'm perfectly happy with decimal approximations to things. Occasionally I'm just curious and interested and go try to find these myself, but that's all it is for me, is a curiosity, because I'm more interested in how far is it to fly around the sun, like a practical problem. So I want 4.64 and let's get on with it. So these are all the interesting things. I've sort of asked all the interesting questions that I think you can ask about your flight, around your elliptical flight. So let's just go, I don't know, maybe practice that a bit. In a sense, I've showed you everything we need, but let's just look at another example. Let's kind of pick something a little less hassle. So let's look at another example. X, and let's make this one a little bit more friendly. Anytime you get sine and cosine involved, you're asking for pain. But the problem is you get way more interesting graphs. I wonder what this is going to look like. So you see, squared equations, and so maybe you're thinking, some kind of a parabola or something like that. But let's go fly along this curve a little bit. I'll bring a graph in. So I say t squared minus 12t comma, what's this graph going to look like? It's very exciting. T squared plus 8t minus 20. Boom. We got a graph. Except for we don't have a graph. Why don't we have a graph?
Gotta zoom out.
Yeah, maybe zoom out. So this is going from 0 to 1 second. So maybe it's just further out and I just can't see it. That's the first thing to check, right? Oh, there it is. And as I showed you before, it's to determine directionality of this is kind of a pain, because you actually would have to put in t is 0 and then t is 1 and t is 2, and kind of you could plot those points and then that would show you directionality, but it's just so much more fun to kind of watch it happen here. So so it's actually starting at 0, -20, if you will. If it starts flying from 0, -20. And kind of cruises up there. But I would like you to understand that there is such a thing as negative time. In other words, I'm going to go back down here. I wonder if I can do this and just put negative c. So, if I started further out, and maybe I'll just go type something now, like say -12 or something like that. And we'll fly out to 20. So there's a part of its path. So directionally, it's flying clockwise again. Do you notice that? It's flying clockwise. And so that is kind of ellipse, but it's kind of fun because it's sort of a sideways ellipse. So I could do all the same things with this that we just did a second ago. I could determine speed at different places on that flight. I could determine the area under that curve. But notice in this case, the area under the curve isn't quite so kind of nice. Because now I'm thinking, and remember, it's no different than before. It's actually the area under the curve from the curve down to the x-axis. So because this is not enclosed, I find myself a little more confused by that, you should think. And I could find arc length. I could find all kinds of fun things about it. And so let's just go find a few of those. Let's see. I think we can content ourselves with that graph. But why don't you because one of the things this particular graph is really good for is notice it has a horizontal and a vertical slope. There's a place where the slope is infinite, and there is one place where the slope is 0. See if you can find those. I'm going to give you a head start. This is a good kind of a test question, in my opinion. Find the point where the slope is vertical. Find the point where the slope is horizontal. Perhaps we'll get lucky and there'll be whole numbers, but I made this up, so I doubt it. So it's got directionality. I'm going to let it live between t is 20 and negative 12. When you call time negative, that sort of feels troublesome, but that's not terribly troublesome if you just think of time as now and then any time before you, like 12 seconds ago. And of course, because I gave you a graph, you should kind of be able to verify the accuracy of your calculation. I'm thinking that the horizontal tangent, which is about right there, to me, looks like it should be about 60, negative 40, somewhere around 60, negative 40. It doesn't actually hit down there, but maybe 60, negative 36 or something. I don't know. I'll probably fix this, but I'm just guessing. 60, negative 36. And vertically, I'm guessing negative 38, 60. If we're lucky, I'm correct. And those are perfect whole numbers. If we're not lucky, they'll just be close enough to kind of check our work. So our derivative of x is 2t minus 12. That seems easy. And our derivative of y is 2t plus 8. So we said our horizontal slope happened when the numerator was equal to 0. That happened when 2t plus 8 is equal to 0, which apparently happens at t is negative 4. Notice what we found is a time, not a coordinate. We'd have to go plug t is negative 4 into our problem to actually see what point I'm at. So it is at t is negative 4. So I need to find x. of -4. 16 plus 48, is that right? 16, yeah, 16 plus 48 is 64. So that kind of fits. That fits the 60 that I guessed. And if I look closely at my graph, I think, well, that actually was a little past 60, so doesn't surprise me. And my y value, not y prime, but my y value of -4 would be 16 minus 32 would be -16 minus 20 is -36. So I actually got the y coordinate correct. So cool, 64, 36, cool. There's the place where it is actually horizontal, it agrees with graph. I don't need anybody to check my work. I'm sure that I got that right. That feels good. And what about the vertical slope?
Forget your negative sign on your set.
Thank you. My 36 is supposed to be negative. What about my vertical slope? We said that was when the denominator was equal to 0. And that's when 2t, and since the slope is actually equal to y prime over x prime. So it's when the denominator was equal to 0. So when is 2t minus 12 equal to 0? Well, that's easy. That's t is 6. So really cool, nice whole numbers. That's why this makes a good test question. Don't come out with a bunch of weird answers. It's exactly 6 seconds, positive 6 seconds. And remember on the graph, this was t equals 0. So -4 is kind of back in time to our horizontal slope of 0. And now we're going forward in time, 6 seconds. Okay, well, that's easy. I just got to plug 6 in. Stick 6 into the original equation. 6 squared minus 12 times 6. So 36 minus 72 is -36. So I got -38. So that seems to be close. And then my y value evaluated at 6. Again, I plugged that into my head. 36 plus 48, 84 minus 20, 64. I think I got that right. So it's the point -36, 64. That's cool. So it came out whole numbers. We got lucky. Now that I think about it, though, since the derivatives of these were t's and not t squareds, then it would make sense they're going to come out as whole numbers, or at least pretty reasonable fractions. And so now I can go kind of fix this and say, yeah, that seems reasonable. And yeah, that seems reasonable. Let's see, what else did we just do that would be interesting to calculate here?
Could do the arc length.
Yeah, I agree. An arc length seems like a good idea, isn't it? So let's find the arc length. And of course, I have to tell you where. Well, in our case, we already limited this to -12 and 20. So again, I'll give you a head start. What's the arc length? How far did this travel? From -12 to 20. It's kind of amazing to think we could find a distance that's curved like that. I hope that the beauty of that isn't lost on you. So we had these derivatives earlier, and we said the arc length is those derivatives squared, added together and square rooted. So we say I'm working from -12 to 20, and I want to take, doesn't matter, since we're adding them, it doesn't matter which is which. So I'm going to put the x prime value first. I can't remember which way I wrote the formula. And the y prime value second. And square them, add them together, and square root them. So again, I'm in one sense, I'm done. Could you do this by hand? Now that trig is gone, you might think, oh, maybe. I'm at least going to rewrite it. Let's see, that'd be 4t squared minus 24t. That'd be minus 48t plus 144. 2t squared out would be 4t squared again, plus 16t, but doubled, and then plus 8 squared. And so, again, this is a total waste of time to redo all of this when it's the same exact problem, if I'm just going to cheat anyway. Minus 48t plus 32t is minus 16t. 144 and 64 is 210, I think. And so no change in the question. The answer is this is very hard. I don't know if you remember doing this, but this requires a trig substitution. This is just flowing back into my mind. We might have to complete the square on that and do some kind of a trig substitution, because this has a Pythagorean theorem kind of a look. And so I think this would be possible, but again, it'd be very painful. I don't want to do it. So arc length produced difficult integrals to take back in Calc 2, and it produces difficult ones here as well. On a test, I would say either just write the integral out, or I would just say evaluate it with software or something. I find it unsatisfying, even though we just did the hard part, if that really is considered hard. I kind of want a decimal. I want to actually get an answer to this. I want to be able to look at the graph and kind of go, does that look right? In the interest of time, let's do this really quick. This time I will put it in the graphing calculator. I don't care. You have access to Desmos and your graphing calculator on tests. And so we were in here jinking around. Let's see. Notice in our case, like I'm in parametric, but does it make sense? We really have an equation that just has like one letter in it. I actually don't, oddly, I don't want to be in this mode anymore. I want to go back to function mode. Oops, that's not right. Because I really just have one equation. And so I'm really saying I have the square root of, well, it doesn't matter what the letter is, x squared. It's probably a good thing we're doing this, except it was 4x squared, right? 8x squared or something, I can't remember. So it was 8x squared. I'm just going to type over the top of that. And then it was minus 16x or 16t. So the fact that I don't need to be in parametric mode, I don't necessarily think is obvious to do this. As a matter of fact, I don't want to be in parametric mode. So there's the square root of all that stuff. I graph it, but you might notice if you graph it, this has to be able to go from -12 to 20, and my y coordinate is not big enough to do this. So if I ask it to find the integral of this, it's not going to do it. So I need the window to be large enough. So my x coordinate in this case was 20. So this has got to be at least 20. I'll make it 22. And my y coordinate, or my smallest x, was -12. So I need that to be -12. I'll make it -15. So x is all I really care about. Now, if I graph this, I might not see y because the y is not high enough. So I don't even see a graph. And of course, that kind of makes sense because the numbers are so huge, right? So, but it's kind of bothering me a little bit. So I'm gonna go put 500 down here, and maybe that's way too big. I have no idea, but hopefully I won't have to do it again. So, I get really big numbers for this. And so it's a square root of a parabola. Now I can see that I'm, way too high. So again, just because I want to illustrate some things to you, it looked like, I don't know, maybe 120 would have been enough. So we'll at least be able to see it. So the area under this curve is actually the arc length. This has nothing to do with the original graph. In other words, this area doesn't mean anything. This area is an arc length. Isn't that weird? So anyway, right there, calc above trace. You hopefully know this from before. Second calc, calc 2. Number 6 is calc 1. Number 7 is calc 2. It says, what's your lower limit? We said -12, which shows on the graph. So this is going to work. And what's your upper limit? 20. That shows on the graph. So this is going to work. It's going to show us the area under that curve, which for us is the distance. So we got about 917. Arc length. And so let's go back and look at the graph. This is going to be very hard to estimate, but it just seems like we should at least stare at the graph for a little bit and think 917, is that reasonable? Like what does our graph look like again? Because it's curved, I'm going to have a very hard time estimating that. That's kind of the idea. But what a big number, like 1,000 makes sense here. Well, look at the ordered pairs. So this is out at, roughly 300. And then it cruised all the way back to, well, -36. And so it's like 336, but curved. So like 340 maybe across to there. I just got it to here. Do you agree with that? So I just made it a little longer. So it's horizontally, it's 336. And so I said, well, it'd be a little bigger than that because it's curved. And actually, now that I look at it, I think that's probably a bad estimate. Maybe it's more like 360 or something like that. And then it cruises up to here. Well, the y coordinate of this is 64, and that y coordinate's like 550. So that's like 500. So it's kind of like 500 and 360, so like 860. Oh yeah, it would be kind of big like that. It would be kind of big like 917. And so obviously it does look reasonable, doesn't it? But notice that's the best I can do. I mean, I can't check it, but at least it's like, yeah, well, it would be a big number. That's kind of cool. It's a curve. We wouldn't be able to get this without calculus. That's kind of neat. Just because we need the practice, we better come up with an area problem for this as well. But I wonder what it's going to tell us if we just do the area from -12 to 20. Do you find that a little confusing like I do? In other words, area under the curve isn't going to find like, well, that area right there, which I think of as positive, and then that area right there, which I think of as negative, and then kind of all of this area up here. And the question is it going to keep track of negatives and positives? What is it actually going to produce? Like what happened back here with this ellipse a minute ago? Apparently it isn't keeping track of positives and negatives, because if it had found the area on the top half of this, I need to move that. If it had found the area on the top half of this, which is positive, and the equal area on the bottom that was negative, does it make sense? It would have said 0 is the area. So apparently that's a little weirder than what we're used to. So I'm a little curious. I'm not really sure what this is going to produce. My gut reaction is to think, well, let's not go from -12 to 20 because I'm going to get an answer. I'm not really going to be sure what it is. What do you think it's going to do?
I wonder if it's like finding the area to the origin, like the closest line to the origin, and kind of like going around in a circle. I don't know.
Yeah, I mean, it was based on rectangles. That's the thing that's bothering me is, and we're going to talk about this in polar in a little bit, but it it was based on rectangles. And so, it sort of feels like there's part of me that wants to think, it's just going to find the area like in this whole space right here. Does that make sense? It's going to find that area. It's kind of weird. I'm not really sure what to make of that. Just for the practice though, let's see if we can kind of figure that out. Let's just do it from t is 20 to -12. Just see what happens. I mean, we're going to be able to plug it in and get an answer. We're just not sure if we know what the answer means, right? So again, let me give you a second to just get a head start on that. What was the formula for that again? And given that this was our X and this was our Y, what did we do? This is an example of a note that I would be putting on the test for you because we have other things to study. And by the time we're done with this, it won't be stuck in your head quite so easily. But we said the formula for the area was the Y coordinate. So some function of Y, again, I have lots of ways I could write this. I'll just say Y of t unchanged, but then times the derivative of the X coordinate. That's what the formula was. That's our formula. Oh, okay. So since our Y formula, we have both of those. Since our Y formula was t squared plus 8t minus 20. And our X derivative, the derivative of our X coordinate we already did was 2t minus 12. And okay, this isn't hard. I've got to multiply those. So again, the question kind of becomes, is this an integral I can take? Well, I've got to multiply these two things together and I have to distribute. So 2t would get multiplied by everything. So that would be 2t cubed. And then 2t times 8t would be 16t squared. And 2t times 20 would be -4t. And then 12 times everything. So minus 12t minus 96. Sorry, minus 12t squared. -12 times 8t would be -96t, and -12 times -20 would actually be 4. What is that? 240, positive 240. And so if I collect the terms together, I get a 2t cubed, and I get a 4t squared, and I have a -40t and a -96t, which is -136t. And a plus 240. And so I think, oh, that's kind of fun. This is actually an integral I can take. This is not one I need to cheat on. Although if you let me, I'm going to anyway. Because even though I know what I'm doing and so forth, you should think I might screw this up. But this is kind of fun since we can actually do it. Let's do it. So I power rule. Remember, this is like, hey, this is what we just studied. This is a power series in a sense. And so we like these because these are easy integrals to take. So I use power rule. T cubed becomes t to the 4th, and then I divide by 4. So I get 1/4 t to the 4th. T cubed divided by 3. So I get 4/3 t cubed. 136 t squared divided by 2. So that would be, what is that, 18 and 50, 68? Doesn't it not seem right? 140, yeah, 68 minus 68 t squared, and the 240 would grow itself a t. Again, language of calculus. The integral is taken. Do not have an integral sign out here. You're confusing people. Don't leave me in the awkward place on the test of trying to decide whether you should lose points for not being able to speak the language of calculus. Also on the test, I would tell you on this problem, do I want you to waste the time to calculate this by hand? I don't know off the top of my head. It does feel like a little bit of a waste of time to me. Plus now I got to go plug in 20 and plug in 12. And it's like, oh my gosh, I can't even type that in my calculator correctly. So, my chances of getting this right, feel really slim. Does it feel that way to you? I'm cheating right now and typing into my graphing calculator since I made this problem up, didn't prepare ahead of time. I don't know the answer to this yet, but I'm doing that on purpose to give you a little bit of time to try to answer this yourself. So if I cheat and do this, I just graph the cubed equation and then use that second calculate button just to ask it what's the area under that curve. And when I do that from -12 to 20, oops, that's not true. Clear, second quit, second calculate. -12 to So I just used my regular calculator and the window wasn't adjusted out to be out to -12 and 20. And so it wasn't working. So that could happen to you. It's worth mentioning. So if everything is plugged in right, I should get a whole number for this, I think. Let's see, is that true? Not necessarily, because I'm dividing by thirds. So now I got an exact answer to this. 72874, 72874 and 2/3. I can see 0.667. And since I know I'm plugging numbers in with thirds, I know I'm going to get some fraction that's got thirds in it. So I didn't get lucky, but I still got a perfect answer. So again, I just get this gigantic number. Well, of course, my y coordinates were like 500 here. So of course I'm going to get a big number, but I don't really have any sense of whether I got this right or not.
So it did take all of that area, right?
Yeah, that's my.
That's a
It kinda-
lot.
It did kind of seem to take all the area, but is it the green area that I have kind of outlined? Almost like it doesn't care that they're positive and negative. Notice it's such a big number, it's kind of hard to estimate that. So because I'm not actually sure, I'm going to give you an extra credit problem here. The extra credit problem would be this. And I think this is a good one. I'm going to go do this after class because I'm actually not sure all of a sudden, embarrassingly. Does it make sense this is a known point? Like you could know where that was right there? Because that would be where y is equal to 0. So couldn't I go to my equation up here and set t squared plus 8t minus 20 equal to 0 and figure out where that was? And because it's a squared equation, it's going to have two answers, and there would be the other one right there. And so, and then if I put t equals, since this is t equals -12, where all this started, couldn't I put t equals -12 in? And so I could actually know what those points were in terms of x and y, and I could know what point this is. And so my instinct is I'd kind of like to go find area. Oops. I'd kind of like to go find area 1 and area 2 and area 3 like separately somehow and add them together and kind of see if I added all those together, is that the same as that 72,000 number we just got? Or is it not? And perhaps, as I said before, maybe the area is actually kind of somehow between, like it's all of that.
I don't know how you'd split up area 3.
Yeah, so it is the area, again, I'm thinking rectangles, it's the area under the curve. And so what I would need to know is, what value. So I'm at t equals -12, and then I'm at t equals something, and then I'm at t equals something else. And then up here, I know I'm at t equals 20, right? Because I went from times -12 to 20. And so it's definitely finding the area under a curve because I kind of showed you where the formula comes from. And so if I go from these points, let's see.
Oh, I see.
You see what I'm going? So if I do 3 different integrals from -12, from -12 to whatever this time is, then I'll get that area. And again, I would think that's going to be positive. And then I'm going to go from this time to this time, and I would think that's going to come out negative, but it might not, right? Because we're just talking about area. And so, I'm a little unsure, you should think. And then I'll go from this time up to that time, and I should get this area, which is huge. That's the giant majority of this, again, because that's up at like 540 for a height. So no wonder that area is so gigantic. These are really large numbers. And so, what is that actually finding? And so is it positive area plus positive area? So like 1 plus 3 is positive, and then -2, and then that gives us that 72,000 number we just got. What is it actually finding if I just kind of
I could see for area 3, it'd be easier to differentiate with respect to y.
Well, you could attempt to make this a y equals x equation, but the problem is this is fairly hard to do because neither of these two statements up here is very solvable for t, so it's very hard to get rid of t. You need to be able to solve one of them for t and plug it into the other one to get rid of it. So you make it a y equals x equation. And not only that, this graph is not a function. Like, you can't even make this a y equals x equation because your graphing calculator isn't going to graph something where there's 2 different y values for the same exact x. In other words, I'm here at x is 100, and it's like, nope, there's 2 answers to that. Sometimes it's negative and sometimes it's up here as positive. So you can't even put this in the y equals x form and get the entire graph. You could get the top half of the graph separately from the bottom half potentially. You see the rub there? So the only other thing I want to say then, because we sort of burned the whole period, we never even got into polar, which is not good because we're probably going to be behind now. But I just want to warn you, because I was playing around with this a little bit before class. Question 8 in the second set of the kind of the calculus homework is rough. It's not a rough integral to set up, but it's a rough integral to take. It comes out with a nice, easy answer. But that's just a warning. And, we had some rough integrals to take today too, right? Because I made them up randomly and we cheated on many of them. We didn't have to cheat on all of them, but books are going to assume you're still good at Calc 2. Does that make sense? Like they're going to just give you random problems and say, oh yeah, they know Calc 2, so they can take integrals of anything. There's a couple of challenging integrals. There's one of them that's integration by parts. So it's like expecting you to do that. So you might just play around with, can I get that back? Do I have to cheat to do it? My recommendation would be to try to tackle that assignment today. The 12.1 assignment, be done with it today so that to start a class tomorrow, if you want to ask about it or stay after, you certainly can. And then we'll go from there. But the cool thing about this section is it's actually not that hard. The hard part about it is Calc 2. Does that make sense? It's not actually hard to set up what we need to do. It's just hard to potentially do the algebra. Maybe the algebra is hard, or maybe the Calc 2 is hard, but we didn't really learn anything today that's actually that hard in and of itself if we're allowed to cheat and take an integral. But anyway, we're out of time, so we better stop.
Wow, question 8 even taunts you. It says graph it and it'll make you cry. Oh man.
I laughed at that because it produces a graph that's really a neat shape, which is why the cry illustration comes in, but the integral that you have to take will make you cry as well.
Oh no.
I was playing with it before class and I thought, what? This is I mean, I can get this right, but that's pretty tall order for people that are just figuring this stuff out. So all right, we're going to play with polar tomorrow. And It's a beautiful thing if you've never done it before. And then fortunately in polar, 12.2 is just what does a polar equation look like? 12.3 is the calculus of it. So that's kind of nice. So I'll have a couple of days to kind of play around with the polar version of an equation. Neat stuff. All right.